We want to use the AC models of switching converters that we derived last week to design the control systems of power converter systems. To do this, we need to plot the frequency responses that are predicted by the AC models. And in other words, we need to construct Bode plots of the circuit responses. Now, this is something that is traditionally covered in the undergraduate circuits curriculum for electrical engineers, and many of you may already be good at that, and in that case, you can skip this in the next lecture or two. However, I'm going to review Bode plots here so that everybody is up to speed on them, and also I will probably teach you some things that weren't covered in the circuits classes and that go beyond them. So I'm going to go through this material quickly, but I'm going to, I think, cover all the bases. So a Bode plot is a log frequency response plot of a transfer function. So if we have a transfer function, like for example, we talked last week about the control to output transfer function, GVD of S, which was the transfer function from D hat of S to the output voltage, V hat of S. This is a transfer function that is frequency dependent, and to plot it and find the what is called the sinusoidal steady state, we let S equal j omega, where j is the square root of -1 and omega is angular frequency, so that we get a complex valued function, GVD of j omega. We can then find the magnitude of that complex function and its phase and plot those as a function of frequency omega. And when we do that plot, that is the frequency response plot. When it's on a log-log scale, it's called a Bode plot. So for a Bode plot, the frequency axis or horizontal axis is drawn on a logarithmic scale, usually versus the frequency in hertz. And the vertical axis is effectively logarithmic, but it is plotted in units of what are called decibels, where actually a magnitude expressed in decibels is given by 20 times the base 10 log of the magnitude function. Okay, so if we have, say, a gain of 1, so G equals 1, the base 10 log of 1 is 0, and we get 0 decibels. If the function is 10, the base 10 log of 10 is 1, and we get 20 decibels. And in fact, increasing the function by a factor of 10 adds 20 decibels to the function expressed in dB. So we'll plot the function in decibels on the vertical axis. Here's some common numbers and their values in decibels. A factor of 2 turns out to be 6 decibels. A factor of 10 to some power is 20 times the power in decibels. So 1,000, which is 10 to the third power, would be 3 times 20, or 60 decibels. If we want to plot a function that has units, such as an impedance or a voltage or a current, formally we should divide the quantity inside the log to make it unitless. And so one formal way to say that is that say we want to plot impedance, we need to divide by some constant impedance that we call the base impedance to get a dimensionless number and then express that number in decibels. Of course, you have to tell everybody what number you decided to use as the base impedance. A very common choice is a base impedance of 1 ohm. So then we would take our impedance, divide by 1 ohm, and then express that number in decibels. If we do that, it's the tradition to call that Z expressed in dB ohms, like this. So 5 ohms, if we have it with a base impedance of 1 ohm, 5 is 14 dB, right here on this plot or chart. And so 5 ohms would correspond to 14 dB ohms. You often see currents for electromagnetic interference specifications. You see currents expressed in dB microamps, and what they're doing there is they're choosing 1 microamp as the base current. So 60 dB microamps is 60 dB, or a factor of 1,000 with respect to 1 microamp, which means it's a current of 1 milliamp. The usefulness of the log-log plot for Bode plots is that functions that go like frequency to some power are effectively straight lines when we use this log-log scale. So for example, if we have a transfer function g whose magnitude is frequency divided by some constant f0 to the nth power, then when we express that in decibels, we take 20 times the base 10 log. The power can be taken outside, and we get 20 in times the log of f over f0. So this turns out to be a straight line in log f. So here effectively you can think of the horizontal axis as going like the log of frequency, and we have a function here that varies as the log of frequency. And in fact, if you increase the log of the frequency by 1, then we'll increase the magnitude by 20 times n decibels. So we say that we have a slope of 20 in decibels per decade, where a decade is a factor of 10 in frequency that increases the log of f by 1. So here is a plot for several different values of n. So here for n is 2, our function is f over f0 squared. We have a straight line with a slope of n times 20, or 40 dB per decade. And the function actually goes through 0 dB right here at f equals f0. When if you plug in f equals f0, you get 1, and the base 10 log of 1 is 0, so we're at 0 dB when f equals f0. So what we can do then is just take one point that is 0 dB at f equals f0, and then draw a line with the correct slope through that point. The big use of Bode plots is to approximate our magnitude function over different frequency ranges by functions of this form. So we may have a function that goes like frequency squared over, say, frequency range from here to here, and we'll follow this curve. And then over the next frequency range, maybe it goes like frequency to the first power, and so from there we'll go with a lower slope, and so on. And so we divide our frequency response plot into different regimes or different frequency ranges where we have different slopes. Okay, let's do an example. Here's a simple RC low-pass filter circuit. So our output voltage, V2 of S, is equal to the input, V1 of S, multiplied by the circuit transfer function. And the transfer function of this circuit is a voltage divider equal to the impedance of the capacitor, which is 1 over SC, divided by the sum of the impedances, R plus 1 over SC. Okay, so that's what we have here. We're going to write our transfer functions from now on in a normalized form as a rational fraction that's in normalized form. What I mean by a rational fraction is that it's a ratio of polynomials. So there's a numerator polynomial divided by a denominator polynomial. And what I mean by normalized form is that the coefficient of s to the 0 power is 1 in both the numerator and denominator. So here if you multiply top and bottom by SC, then what we get is 1 in the numerator, and in the denominator we get 1 plus SRC. So this is a nice normalized form rational fraction. Okay, this term coincides with a standard form that we're going to use for a first order polynomial in the denominator. This is called a pole, in which there's a root of the denominator. And the normalized form that we will use has, again, the coefficient of s to the 0 power is 1. And here we have a constant omega naught that tells us the coefficient of s to the first power. Okay, by equating our standard form to the original function, we can find that 1 over omega naught is equal to RC. And so this gives us an equation for the coefficient omega naught in our standard form, and its relationship to the elements of the original circuit. Okay, so we have our G of S then is of, for the simple pole, is of this form. To find the magnitude of this transfer function, we let S equal j omega, which gives us this, and then we find the magnitude of the resulting complex function. So the complex function g of j omega at any given value of omega is some complex number that has a magnitude and it has a phase. So we can find the magnitude by the magnitude would be the square root of the sum of the squares of the real part plus imaginary part each squared. If you multiply top and bottom of our function by the complex conjugate, 1 minus j omega over omega naught, you can express g like this, and this part here is the real part, whereas this part here is the imaginary part. Okay, so to find the magnitude then, we find the square root of the real part squared plus the imaginary part squared. If you plug those real and imaginary parts in and do some algebra, you can show that the magnitude works out to be this function. There's actually an easier way than that. If we have, say, g is some numerator polynomial divided by a denominator polynomial, the magnitude of g turns out to be the magnitude of the numerator divided by the magnitude of the denominator. So the magnitude of the ratio of the polynomials is equal to the ratio of the magnitudes. So all you really have to do, since the numerator is 1, its magnitude is 1, all you really have to do is find the magnitude of the denominator, which has this real part and this imaginary part. So what we would get then would be 1 over the square root of the real part squared plus the imaginary part squared, omega over omega naught, quantity squared, as the magnitude of g. I would also note that you don't include the j when you square the imaginary part. If you did, that would give you an extra minus sign, which is not correct. Okay, so here is our magnitude function. We now express that in decibels. So 20 times the base 10 log of this. Is that. We can use the property that the log of 1 over x is equal to minus the log of x. So we can actually flip over the quantity inside the log and pull a minus sign out instead. So this is up to the minus 1 power. And we can get this expression for the magnitude in dB. Okay, here is our function that we found for the magnitude. What we're going to do next is draw the Bode plot by approximating it over different frequency ranges by functions that go like frequency to some power. And in the case of this simple form of the single pole, we find the asymptotic behavior at low frequency and high frequency. So at low frequency, which means in particular for frequencies where omega is very small, what does this function tend to? Well, if you look at the denominator, we have 1 plus a function of omega, and when omega is small, this function of omega becomes small. And in particular, when omega over omega naught squared is a lot less than 1, we can just throw out this term. So another way to say that is for omega much less than omega naught, the function we just ignore this term and we get 1 over root 1. So magnitude of g goes to 1. And that's the asymptotic behavior. So our low frequency asymptote we're going to draw as just a straight line equal to 1 or 0 dB. How about the other case? What happens at high frequency? So if we reverse the inequality, where omega is much greater than omega naught, in that case, the omega term becomes large compared to 1, and we can throw out the 1. So then we get 1 over omega naught squared, which goes to 1 over omega naught. Or this is a function that goes like omega over omega naught to the minus 1 power. If we want to express this in frequency f, omega is 2 pi f, so we could write this as 2 pi f over 2 pi f naught, all to the minus 1 power, which is just f over f naught to the minus 1. Okay, this is a term that we've already seen. If we go back a few slides, here was our plot for functions that go like f to some power. Here the power is n is minus 1. So we'll have this curve right here, the n is minus 1 curve, and it's actually a line that has a slope of minus 20 dB per decade, and it goes through 0 dB at f equals f naught. So here is that line for f much greater than f naught. We have the minus 20 dB per decade slope, and it passes through 0 dB at f equals f naught, which in fact intersects the other asymptote. So we have two different asymptotes, one for f much less than f naught and the other for f much greater than f naught. The only thing left is to say, well, okay, what does the exact curve do in the vicinity of f equals f naught? And to find that, we can just plug in some values. So for example, if we when f equals f naught, what do we get? Our magnitude of g then becomes 1 over root 1 plus f over f naught quantity squared with f equals f naught, and the whole thing will go to what? 1 over root 2. Okay, 1 over root 2 expressed in decibels works out to be minus 3 dB approximately. So at the corner frequency, the function we say is 3 dB below the 0 dB asymptote, or we say the function is 3 dB down at the corner frequency. You can do a similar calculation at f is 1/2 f naught or f is 2 f naught, so a factor of 2 on either side in frequency, and find that the exact curve is 1 dB below the asymptotes there. So we can plug in then those values. You just draw the asymptotes and then plug in the values for these 3 points and draw a smooth curve through them, and that is the plot of the single pole response. So anytime we get a term that can be written in this form, then this is what its magnitude looks like. Okay, we should also talk about the phase. The phase is very important in design of the control system, so we need to similarly understand the phase. So here is, again, our g of j omega is this. To find the phase, this phase angle, we know from geometry the phase is the arctangent of the, in this case, the imaginary part, or this opposite side divided by the real part, which is this side. So from trigonometry, we get that the phase is the arctangent of the imaginary over the real part. When we take this imaginary part and this real part and divide, including the minus sign, we get that the phase is the arctangent of omega over omega naught, which is the same as minus the arctangent of f over f naught. Here's a plot of that with frequency again varying on a log scale. This is a computer-generated plot. We can plug in some values. So as in the magnitude, we might look at the asymptotic behavior. What happens to this function for omega much less than omega naught? Well, we find that the function tends towards a 0-degree asymptote at low frequency. And likewise at high frequency with omega much greater than omega naught, the function tends towards a constant asymptote of minus 90 degrees. At the corner frequency omega equals omega naught, you get minus the arctangent of 1, which is minus 45 degrees. So right here at the corner we're at minus 45. So we have asymptotes for low frequency and high frequency, but unlike the magnitude case, the asymptotes don't intersect. And we need some kind of other asymptote to draw for mid-frequencies that tells us how the phase changes between the high and low frequency asymptotes. Now there's more than one way to do this, and in fact in different textbooks or different papers and things you'll see different choices for that asymptote. One way to do it is to find the slope of this function right at the corner. So right here at minus 45 degrees we could differentiate the arctangent function and find its slope. It's actually a little tricky because you have to vary frequency on this in this logarithmic form and then take the derivative of that. But we can do it, and if you do that, it turns out that if we draw a function with that slope and extend it up to the high and low frequency asymptotes, then this break frequency where the asymptotes intersect turns out to be equal to e to the pi over 2 times f naught. And this one here turns out to be e to the minus pi over 2 times f naught. Okay, get out your calculators. E to the pi over 2 is 4.81. So if we know f naught, we can multiply by 4.81 and find this break frequency where the asymptotes change. So you'll see in some books that's what people use. In some other books, most notably the Shams outline on Bode plots, they round 4.81 up to 5. And so this is 5 times f naught, and this is f naught divided by 5. Yet another choice that is popular is instead of 5 to use 10. So here's that choice. There is in fact no such thing as an exact approximation. 10 is easy to do in your head, and in fact the choice of 10 is perhaps not quite as good in the vicinity of f naught, but it's maybe a better average approximation of the curve over the whole range. So again, it's a matter of taste, but what we're going to use in here is 10, and it does have the nice interpretation that the phase changes over 2 orders of magnitude about the corner frequency. So it'll change from 0 to minus 90 degrees over 2 orders of magnitude in frequency. And that's a good approximation of how the phase works. So the slope of this phase asymptote then is minus 45 degrees per decade, where a decade is a factor of 10 in frequency. So in this factor of 10 in frequency from here to here, we change by minus 45 degrees. Okay. The actual function deviates from the asymptote by 1/10 of a radian, or 5.7 degrees, at these break frequencies. So here's a summary of the rules for constructing the magnitude and phase Bode plot asymptotes for the case of the simple real pole. So the magnitude asymptotes are 0 dB at low frequency and a minus 20 dB per decade slope at high frequency, with a deviation of minus 3 dB at the corner frequency. The phase asymptotes have a minus 45 degree per decade slope asymptote going from 1/10 of the corner to 10 times the corner frequency. The low frequency asymptote is 0 degrees and high frequency asymptote is minus 90.